Homework 10, Quadratic Functions, Video 5. In the previous video, we sketched the graph of a quadratic function that was in general form by finding the vertex, finding the axis of symmetry, finding the y-intercept and its mirror image, its reflection across the axis of symmetry, and finding the x-intercepts. Let's do it again for our other quadratic function that we've been using, -3 times the quantity x minus 1 squared plus 7. And we've already found the vertex. Recall that if you are in standard form, vertex form, the vertex is embedded in the function. The number after the x, change its sign, that's the x-coordinate of your vertex. The number at the end, keep its sign, that's the y-coordinate, so the vertex is 1, 7. Now, unlike the previous video, I kind of already worked this one out in advance so that I know how much space I'm going to need. My vertex is going to be all the way up 7, but this parabola is upside down, so that's the highest it's going to go. Now the x's aren't going to have to go very far left or right at all. In fact, all of the x's of interest will be positive, so I won't need any negative room on the x-axis. So let's sketch this one. 2, 3, 4, 6, 7, 8. Might need to go down here a little bit. Actually, we won't. And for the x's, we don't need to go very far left. In fact, we won't go left at all. And then 1, 2, 3, 4, 5. That should do. Okay. So let's start by plotting the vertex, which is over 1 and up 7. So 1, 2, 3, 4, 5, 6, 7. And again, this parabola will be upside down because the a is negative. I say upside down, who's to say which is which? It opens downward. And I can also set up the axis of symmetry by dropping a vertical line. I got a straight edge, why don't I use it? By dropping a vertical line right through the vertex. Done better jobs, but I've done worse. So our axis of symmetry is going to be x equals 1. Let's find the y-intercept. Remember, to find the y-intercept, you just have to substitute 0 into the function. This one is going to require a little bit more work because before we do anything to the 0, we're going to subtract 1 from it, so it won't kill everything it touches. But it's not that hard. Just follow the order of operations. Parentheses first. 0 minus 1 is -1. Exponents next. -1 squared is 1. Multiplication next. -3 times 1 is -3. And then finally addition. -3 plus 7 is 4. So our y-intercept is going to be at 4. So go up 4. 0, 4. And the mirror image of it. Now this one's a little bit easier because our axis of symmetry is at x equals 1. That means that the y-intercept is 1 space to the left of the axis, so its mirror image would be 1 space to the right. So where would that put us? It would put us at 2, 4. It's going to be a skinny parabola. Now let's find the x-intercepts. I'm going to warn you, finding the x-intercepts is going to be a little bit irritating. And I'm going to go ahead and make some room for it. It's not difficult, it's not something we haven't seen before. But to find the x-intercepts, you have to solve the function equal to 0. Again, that will be a recurring theme for many sections to come. So if we put the function equal to 0, -3 times the quantity x minus 1 squared plus 7 is equal to 0, we have a quadratic equation. Or we have ways of solving them. We could try to bust it open and use the quadratic formula. We could bust it open and try to factor it. But recall that when you're solving a quadratic equation and there's only one x term, you can solve it just by stripping everything down and hitting it with the square root when the time is right. So because this has one x term, I'm going to solve it by isolating the x. The first thing to go is the 7. Since it's added to both sides, we'll subtract it from both sides. and be left with negative 3 times the quantity x minus 1 squared equal to negative 7. Not liking all these negatives. Next move is to divide by negative 3 on both sides, which cancels the negative 3's on the left, leaving the quantity x minus 1 squared. And on the right side, we get negative 7 over negative 3, which won't reduce, but negative divided by negative is positive. So those two negatives are gone. Then hit both sides with a square root. But don't forget, when you're solving an equation and you square root both sides, you have to use plus minus on the right side. Well, technically, it doesn't matter which side. I put it on the side where the x isn't. Speaking of the side where the x is, the square root cancels the square and leaves x minus 1. Now, what do we do with the square root of 7/3? For now, nothing. We'll just leave it parked under the square root with the plus minus in front of it. And then if I add the 1 to both sides to cancel the plus 1 on the minus 1 on the left, we get x equals 1 plus or minus the square root of 7/3. Oh boy, look at our x-intercepts. They're nice and ugly. Where in the world are they on this picture? Well, if you're plotting points on a graph, answers like 1 plus or minus the square root of 7/3 are useless. So I went ahead and put both of these into a calculator. The one problem with the subtraction and the one problem with an addition. If you do 1 minus the square root of 7/3 correctly in a calculator, you get about negative 0.53. And if you do 1 plus the square root of 7/3 in a calculator, you get 2.53. So I can estimate where those are on the x-axis. This is about negative 1/2, so I'm just going to go backwards a half, put a dot there, and label it negative 0.53, 0. And then the other one is about 2.5 to the right, so 1, 2.5. 2.53, 0. And now I have my 5 points for my parabola. Gee, this parabola is a lot skinnier than the previous one. Wonder why that happened. Let's go ahead and pull off the domain of range before I tell you why this one's skinnier. The domain is a trick question. For a quadratic function, it's always negative infinity to infinity. For any polynomial function, the domain is always negative infinity to infinity. But because this parabola opens down, the range is going to stop at a certain point. The range is bottom to top. This graph goes down forever, so the range begins at negative infinity. And the highest y value is 7. Now, why is this parabola skinnier? Well, there's one number in this function that we didn't use much, and that was the negative 3. Now, the negative did tell us that it opened down, but what about the 3? The number in front of the x squared, the a if you will, dictates how wide the parabola is or how skinny the parabola is. It's kind of hard to show where the number 3 is on this picture. It's not impossible. If we had unlimited time, I could actually show you how this number is applied. But here's the general rule. The larger this number is in size, the skinnier the parabola. And vice versa, the smaller it is in size, the wider the parabola. Like if this had been a negative 1/3, a fairly small number that's negative, then it would have made the parabola a lot wider. If you just really want to know where the 3 is in this picture, I'll show you, but what I'm about to show you is not something you're held accountable for. This number almost acts like a slope, but just for a brief moment in time. From the vertex, it tells you if you go one left or one right, how far up or down to go. But it only works that one time. It doesn't do it again. Like if I go over 1 and down 3, I'm not going to be here because it's not a line. But it's almost like I'm the slope, but just for a brief moment from the vertex in both directions. If that made sense, great. If it didn't, don't worry. It's not something you're held accountable for.